Hi, I'm Chad with Mastercam, and in this video we'll be working with a part that was modeled in SolidWorks. It's based on an optical mount that's used in military applications. Since there are no curved faces on this part that will require surface machining operations, this part can be cut with flank and face milling from start to finish. This part is going to be machined from 17-4 stainless, and we will be using a 5-axis vise for work holding. Because this part was modeled in SolidWorks, we're going to use the Mastercam for SolidWorks add-in when creating these toolpaths. Mastercam for SolidWorks is free for any Mastercam user that has a Mastercam license and a copy of SolidWorks. Using Mastercam for SolidWorks allows the engineer and programmer to work in the same interface with the same CAD tools. One of the many benefits of this workflow is that if something changes in the design of the part, it's easy for the programmer to update any operations to reflect those changes. As an example, let's take a look at this simple operation on the back of the part. This is a multi-pass contour finishing toolpath, which is being used to finish the faces in this small pocket. If there was a design change after this toolpath was created, let's say the engineer removed the rib from the rear of the part, the toolpath would automatically be marked dirty since the geometry associated to the toolpath has changed. Thanks to associativity checking, the programmer can simply regenerate the dirty operations and the toolpaths will update to use the new geometry. Associativity checking works with all mill, lathe, and router toolpaths. It can be enabled and disabled from the ribbon by clicking on the associativity icon. Because this part was modeled in SolidWorks, we're going to use the Mastercam for SolidWorks add-in when creating these toolpaths. Mastercam for SolidWorks is free for any Mastercam user that has a Mastercam license and a copy of SolidWorks. Using Mastercam for SolidWorks allows the engineer and programmer to work in the same interface with the same CAD tools. One of the many benefits of this workflow is that if something changes in the design of the part, it's easy for the programmer to update any operations to reflect those changes. As an example, let's take a look at this simple operation on the back of the part. This is a multi-pass contour finishing toolpath, which is being used to finish the faces in this small pocket. If there was a design change after this toolpath was created, let's say the engineer removed the rib from the rear of the part, the toolpath would automatically be marked dirty since the geometry associated to the toolpath has changed. Thanks to associativity checking, the programmer can simply regenerate the dirty operations and the toolpaths will update to use the new geometry. Associativity checking works with all mill, lathe, and router toolpaths. It can be enabled and disabled from the ribbon by clicking on the associativity icon. Mastercam for SolidWorks takes full advantage of SolidWorks assembly files. The assembly tree shows all the individual components that are active within this assembly. The finished part file, some defeatured models used to simplify the programming process, the prepared stock, and a subassembly for the 5-axis fixture setup. Here, the defeatured models are created from part copies, which reference the finished part file. Any changes to the finished part file would prompt changes to the in-process models, which would then prompt changes to the corresponding Mastercam for SolidWorks toolpaths. The OptiRough toolpaths in this process reference these SolidWorks assembly components as machining geometry with a certain amount of stock to leave behind. We can also select the fixture setup to be used as an object to avoid altogether. We can create a Mastercam stock model referencing the prepared stock component in the SolidWorks assembly tree. Any changes to the prepared stock component would prompt a change to the stock model and any subsequent toolpaths that reference the stock model. The purpose of the stock model here is to accurately inform our dynamic OptiRough toolpaths of what material is left on the part. As you can see, the first OptiRough operation immediately engages with material instead of machining the open airspace around the stock model. After the first two OptiRough operations, we create an updated stock model that can be used to inform the operations that follow of what material remains. As we move through the process, the stock models will become more complex, yet there is never any wasted motion. From this point, we create more roughing operations, adding in as many stock models as needed to keep the tool motion as efficient as possible. tapered flange on the front of this part was created as a lofted solid, which makes it possible to be machined using a swarf toolpath. In this example, we've created a simplified piece of geometry to make the toolpath creation even easier. First, we will open our swarf toolpath and select a tool with a long enough flute length to machine the edge. On the second page of the operation parameters, we can select SolidWorks solid faces to be used as drive surfaces. Because this is a SolidWorks model, any changes to these original faces will prompt an immediate change to the Mastercam toolpath. If the tool is cutting from the wrong side when the toolpath is generated, we can correct this by toggling the swap checkbox in the cut parameters. Once the tool orientation is corrected, we can add as many multi-passes and depth cuts as required. Finally, we determine our linking strategy to control the tool's behavior on approach and retract. At this point in the machining process, we need to finish the side of the part. Because of the irregular amount of material that's left in this area, we'll use a 2D dynamic toolpath for its ability to rough and finish at the same time. A series of OptiRough toolpaths have been used to get the part to its current state, and we can see the remaining material in process by toggling the display of our stock model. To make geometry selection for this operation easier, I've altered a copy of the original finished part model. With the model displayed, we can launch 2D Dynamic Mill, which opens the Geometry Selection Manager. The first thing we need to do is select the correct tool plane, which orients the tool normal to our desired machining face. Below the tool plane selection, there are 4 different types of regions that can be selected: machining, avoidance, air, and containment. First, we select the machining region, which is the area that we want to machine. After we're done selecting faces in the SolidWorks Selection Manager, the geometry is passed into Mastercam's Chain Manager, where it can be turned into a toolpath. At this point, if we proceed into the toolpath cut parameter interface, we can instruct the tool to either stay inside the machining region boundary or come from the outside. Since the face isn't the bottom of a pocket, we'll start with from outside. We now have the option to preview the finished machining regions. The area that would be machined is shaded red, the area that is seen as open air is shaded blue, and any boundaries the tool is not allowed to cross will be yellow. By toggling the model transparency, we see that there are machining areas that should be avoided, as well as areas of the finished part that are currently seen as open air. Let's solve the first problem with an avoidance region. By selecting the faces to avoid in this interface, the toolpath preview will adjust. Done correctly, the area to avoid will not be red or blue, and it will be bounded by a yellow line. However, this does not fix the false air region on the tapered face of this part. The easiest way to correct this behavior is with a containment boundary. In this example, the containment boundary is driven by a SolidWorks sketch, but it can also be driven by solid faces. Another check of the region chaining preview should show an improved boundary. When satisfied with the preview, we can set up our actual cut parameters and generate the toolpath. Because we're using Mastercam for SolidWorks, the reference model is associative to the original finished model. This means that any changes to the finished model will prompt changes in the reference model, which will prompt us with a change for our toolpath. All the threaded holes on this part need to be thread milled instead of drilled and tapped. In SolidWorks, if we hover the mouse over these holes, we can see that they are M3 by 0.5 threads, with an oversized entry chamfer. The thread mill toolpath requires a series of equal diameter circles to denote the position and major diameter of the holes to be machined. But because this model was created in SolidWorks, we can't select a circle on the body that is equal to the major diameter of the threads. The internal diameter of the model's hole here is equal to the minor diameter of the threads, and the chamfer leading into the hole is oversized. Because we're creating this thread mill toolpath in Mastercam for SolidWorks, selection is a 2-part process. First, we select the geometry in the SolidWorks Selection Manager, and that geometry is passed to the Mastercam Point Manager, where we can sort the order that the holes are thread milled in. As we're entering the toolpath parameters, it's important that first and foremost, we have an accurately defined thread mill. On the Cut Parameters page, you will find all the applicable data needed to machine these threads. New in Mastercam 2020 and Mastercam 2020 for SolidWorks, we can override the specified arc diameter. This means that even though we selected the 4mm chamfers, we can define them as 3mm threads. After entering the thread parameters, we can enter depth values incremental from the top of the holes. Rather than fully simulating the thread mill operation, we can preview the operation by using SolidWorks Section View functionality. This section is both the SolidWorks model and the Mastercam toolpaths. With the thread milling operation displayed on the screen, we can activate the Analyze Toolpath utility. The options for Analyze Toolpath are now docked in the same panel interface as the Toolpath Manager in Mastercam 2020 for SolidWorks. With Analyze Toolpath, we can make sure that the cutter is properly engaged and that the shank is clearing the part, all while reviewing cut parameters on screen. The outer features of this part are finished, so now we can use a series of OptiRough operations to pocket out the internal areas. We have two different cutting tools for these operations, a short 8mm bullnose end mill that is capable of helical entries, and a long-reach 12mm flat end mill that is not capable of helical entries. With tool holder collision checking, we can be sure that the 8mm tool is reaching as deep as it possibly can, while keeping the tool holder safely away from the finished part geometry. We start with a simple OptiRough toolpath from the top plane. Here, we can specify a maximum depth for the tool to reach on this first operation. New for Mastercam 2020, we don't have to provide a minimum or maximum depth if we don't want to, which saves us from spending time on unnecessary steps. Holder checking is turned off by default. As you can see from this Analyze Toolpath image, the tool holder collides with the back edge of the part. If we re-enter the toolpath parameters, toggle on tool holder collision checking, and add an additional clearance value, the tool motion is trimmed down to areas where there are no collisions. It's important to remember that collision checking is only performed on surfaces or solid faces that are selected as machining or avoidance geometry. By repeating this process in all 6 of the part's openings, we can clear out enough material to drop the larger tool into the part without a helical entry. And by creating stock models and rest roughing toolpaths, we can then rough out the material that we could not reach before. Cutting a part like this, sharp corners and burrs are to be expected. Breaking these edges by hand can be inconsistent, time-consuming, and even dangerous at times. Deburring sharp edges on the machine is faster, safer, and completely repeatable. Multi-axis deburr uses a ball-nosed end mill or a lollipop mill to generate a machined edge break of a given size on sharp model edges. We can use this toolpath in any milling machine from 3-axis to 5-axis. The multi-axis deburr toolpath introduced in Mastercam 2019 has received several enhancements for Mastercam 2020. This part showcases the full 5-axis capabilities of deburr with some spectacular results. For example, this deburr path handles the entire inside area of the part in one flowing pass, utilizing the undercutting ability of the lollipop mill. The tool holder is collision checked against the solid body. There are smooth entry and exit moves, as well as a final safe move to the clearance area. To create a deburr toolpath, we first select the solid body. By default, the toolpath will find all sharp edges on the body. We can then select some edges to avoid. The alternative option lets us manually define each sharp edge to be deburred. Let's deburr these 2 edges. Now we define our edge break size. On the tool axis control page, we define whether this should be a 3, 4, or 5-axis cut. For this sample, let's use 3+2. 3+2 will index the cutter to a new orientation for each chain only when necessary, cutting down on extra 5-axis motion. As you can see here, we also have control over the tilt range of the 5-axis cut. We can then define how much collision clearance we would like for the tool holder, shank, and shoulder. Finally, we define our linking and clearance strategies using our standard multi-axis controls. The resulting toolpath is smooth, clean, easy to create, and it did not require manual geometry creation or model alterations.